this particular video, it states that we have an ultraviolet light. It has a frequency of 3.0 times 10 to the 15 hertz. It strikes a metal surface and causes the electrons to be ejected, and those electrons have a maximum kinetic energy of 6.1 electron volts. Part A wants us to find the work function in electron volts. Part B wants us to find the cutoff wavelength. So at what sensitive wavelength does it cause these electrons to move, okay, or be ejected? All right, so here's a diagram. So to help you kind of visualize this, I'm just going to label a few things. The frequency is given to us. The frequency of the incoming beam of light is 3.0 times 10 to the 15 hertz. And then it tells us that, well, the work function is unknown. Essentially, that's what we're trying to find in A. Okay, so I put the work function in the metal surface here because every metal has its own work function. And for this particular problem, we're not given what that work function is for this particular metal surface. It also gives us that these electrons, these ejected electrons, have a kinetic energy of 6.1 eV. Okay, so essentially we're trying to find what this W is. So conceptually, if you know the frequency of the incoming light, you can find the energy. Well, if you know how much energy is coming in, you can figure out how much energy is needed because you have 6.1 eV left over here. Okay, so let's do it. In order to solve for part A, I'm just going to set up E equals KE plus the work function. To solve for work function, I'm just going to subtract KE from both sides, and I'm just going to go ahead and break it up. E is HF, F of the incoming photon, which is given to us, minus KE, which is also given to us. So really here, I'm just going to go ahead and plug values in. H is Planck's constant, 6.63 times 10 to the -34 joules times seconds. The frequency of the photon is given as 3 times 10 to the 15 hertz, minus 6.1 eV, and that is also given to us in the statement. Okay. Now, if you simplify stuff, this right here, 6.63 times 10 to the -34 times 3.0 times 10 to the 15 hertz, those first two terms, if you multiply them, you'll get 1.989 times 10 to the -19 joules, because the unit second here and hertz will cancel out, and it leaves you with units of joules. Okay. However, the 6.1 is in units of eV. So it's important as you practice, make sure you write your units out, and you just cannot assume they're in the same units. So here's joules, here's eV. You cannot just take the difference here because they are in different units. So you need to convert joules into eV, because this question A asks us to find the work function in eV. So I'm going to get rid of joules because I want eV. Well, to get rid of joules, I'm just going to set this conversion factor up. I want to start with what I need to get rid of, which is 1.898 times 10 to the -19 joules times, well, the unit of joules has to go on the bottom, okay, because it needs to cancel. Well, the conversion factor is for every 1 electron volts, it's equivalent to 1.6 times 10 to the -19 joules. So if you multiply this coefficient by 1 and then divide it by the 1.6 times 10 to the -19 joules, you'll get about 12.43 electron volts, right? Because the units to joules cancels out. Well, now that I have that, I can just rewrite this line right here. So instead of this units in joules, I can just go ahead and use the conversion equivalence that I just did, which is 12.43 electron volts minus 6.1 electron volts, and that's the KE given in the statement. So really here, we can find the work function is equal to about 6.33 electron volts. Okay, and that's the answer for part A. All right, part B wants us to find the cutoff wavelength, okay, in nanometers. So I do want to point out, anytime it wants you to find like the cutoff wavelength, okay, and if you know the work function already, because the cutoff wavelength comes from the work function itself, like what is the minimum require, okay, and that's how you should interpret this W. This is the minimum work or the minimum energy needed to start ejecting these electrons, because it uses the phrase cutoff wavelength. I know that I can just look at W. So I'm going to say that W, which is energy, is equal to Planck's constant times V divided by lambda. But this lambda here is the cutoff because I'm using the work function. Okay, this is how much energy you need. This is the minimum energy you need. Because it's minimum, it correlates with the cutoff wavelength. So I already found work function in part A. So really, to find cutoff wavelength, I'm just going to move cutoff wavelength up, and then I'm going to move the work function down. So on the top, I have HV still, and on the bottom now, I have the work function, which I already know from part A. So I'm just going to go ahead and use it. Planck's constant once again, and then V is just the speed of light, And then on the bottom, I want to use the work function that I calculated in part A, which is 6.33 eV. But once again, this here has units of joules on top. This here on the bottom has units of electron volts. So make sure you convert units so that they match before you finish your problem, okay? I'm going to go ahead and convert 6.33 eV to joules. I'm going to start with 6.33 eV. I'm going to put eV on the bottom. For every 1 electron volt, that is equal to 1.6 times 10 to the negative 19 joules. So if you simplify that, EV will cancel out because there's unit on top, unit on bottom. So really you're dividing by 1. So ultimately you're just taking 6.33 times it by 1.6 times 10 to the negative 19. And that'll give you about 1.013 times 10 to the negative 18 joules. Well, now that I have that, I can just go ahead and really substitute out 6.33 EV. Yeah, so I'm just going to say 1.013 times 10 to the negative 18 joules. Well, joules on top, joules on bottom cancels out. Second and second cancels out. So the only unit you're left over with here is just units of meters. So the cutoff wavelength, if you simplify this on your calculator properly, you should get 1.96 times 10 to the negative 7 meters. Okay. However, the question here asks us to express wavelength in terms of nanometers. So you can just convert meters to nanometers on your own, and you should get a value of 196 nanometers. So the wavelength is 196 nanometers. So this is the minimum you need. Okay. Any wavelength longer than this will not work, because longer wavelength carries less energy. So any wavelength longer than 196 will not work. Any wavelength shorter will work. So like 195 nanometers work. You know, like 190 works, 180 nanometers work, because shorter wavelength suggests higher frequency, and energy depends on frequency. So therefore, the higher the frequency, the higher the energy, which will cause these electrons to be ejected and carry even more kinetic energy. So keep that concept in mind. All right, so the answer for this one is 196. That is the cutoff wavelength. You need wavelength shorter than 196 in order for things to be ejected. All right, I hope that helps. Stay nerdy. Don't be whack.